Now this next special case that we're going to consider will be illustrated by the system. 6x minus 2y equals 4, and negative 3x plus y is equal to negative 2. And as I did in the previous example, I'm going to color code the equations to match the graphs. So the red equation is graphed below and the blue equation is graphed below. And I think you're all comfortable enough graphing linear equations that I don't need to go through how we would do that. The bottom line is, though, that both of these equations, graphs, will have a y-intercept of negative 2, and they both pass through the point 1, 1. In essence, they're the same line. Now, you remember that the solution to a system of linear equations represents the point or points of intersection of the two lines. And it's clear that these two lines have infinitely many points in common since they're really the same. Now, you might be tempted to want to write for the solution all real numbers. The problem is that doesn't really narrow down exactly which points in the coordinate plane we're referring to. So in this case, we have to be a bit more formal in terms of how we express the solution. So we do it using set builder notation in the following way. We're going to write then the set of all ordered pairs x, y, such that, and all we need to do is to name one of the equations in the system. So I'll choose the second equation. Negative 3x plus y then is equal to negative 2. So really what we're saying is we want all the points or ordered pairs x, y that lie on the line whose equation is negative 3x plus y equals negative 2. Now we could also have written, if we would like, set of all ordered pairs x, y such that and name the first equation in the system, which is 6x minus 2y then is equal to positive 4. Now I'll give you another heads up here that the special name we give to this kind of a system is that we refer to it as a dependent system. And in this kind of system, the two lines will be the same. And the other way you'll be able to recognize it, which we'll talk about a little bit later also, is that one of the equations in the system must be a multiple of the other. So if you were to look closely here at the blue equation, and if you were to multiply each term by negative 2, I think you can see that you would get the red equation.